Okay, let me continue the lectures about equations with interaction. I will recall the form of equation which we studied last time. It was equation for the family of processes in the finite dimension Euclid space, which has the following form. With the initial condition that we start from every point of the space and mu t is the mass distribution of all particles which are moving according with the process x. So mu t is equal to the image of the initial distribution under the matrix X. So we have the following Cauchy problem. Here, as usual, A is corresponding to the external force, which is acting on the particle which is placed in the point x ut, but this external force depends not only from some older conditions, but it depends also on the mass distribution of all other particles. The same we can say about the diffusion term. W is a Gaussian random measure with independent values on the non-intersecting sets, defined from the product of our space Rd and the time half-life. And you see that this coefficient also depends on the mass distribution of all particles. This calls the name of the equation, which is called the equation with interaction. And last time we discussed the existence and uniqueness of the solution under the usual condition on the coefficients. Usual, I mean Lipschitz condition on the coefficients. What was new? That we have this measure value argument, and consequently we discussed distance between measures. It was Wasserstein distance, and we discussed possibility for coefficients of special kinds to be Lipschitz with respect to this Wasserstein distance of different orders. Then we concluded that we have the unique strong solution to such equation, to such Cauchy problem, and we began to think what we can investigate relatively to the measurable processes which are solution to this equation. Because as we see, when we solve such an equation, what we get? We get the family of random processes, which is indexed by the point for R. And for us, this family can be interpreted as a description of the simultaneous motion of the particles which start from different points of the space. And also, we have the measure-valued process mu t, which is description of the evolution of the mass distribution of our particles. Last what we discussed was the idea of investigation of the behavior of this measurable process, because this is definitely new comparatively to the ordinary stochastic differential equation, where we study asymptotic behavior of the particle. We start from the one point. We start from the one. Here we firstly discuss what we can say about this measurable process. As we have seen from example of the Kuromoto system last time, we cannot expect in general that mu t will have asymptotic stability. So that mu t will tend to some measure nu when t tend to plus infinity. So this is the situation which happens, of course, but it can happen very rarely. The reason is very simple. Mu t is an element, as we said at the last lecture, is the element of the non-locally compact space. It is the element of the space of meshes. So the association can be the following. We just can think for a moment that mu t is a Banach valued or Hilbert valued variable which is evolving in the infinitely dimensional space. And it is not natural to have in the infinitely dimensional space the usual picture of the singular stationary points like focus, node, and so on, set point, which we have in the usual theory of differential equations in the finite dimensional case. From this point of view, it is natural to ask what kind of the limit behavior we can expect from the measure mu t for our equation. Last time I mentioned that maybe we can find the right definition. We can find the right definition in the case when we consider examples. I just recall that when we consider Kuromoto system, where we have a lot of oscillators related to one another, like this sum from J from 1 to N, some sine of phi I t minus phi jt. This is exactly the case of equation with interaction related to the discrete measure we discussed it before. This system demonstrates the following case. We have all these angles leading from the circle. Then the points which are corresponding to different indices E are not demonstrate such behavior that they going to some fixed point. No, but what happened? Finally, they concentrated in a relatively small region, and this region began floating around the circle, but not spread. So one can expect that in general, our measure μt can demonstrate the following behavior. At infinity. At least we can think about it. So I will draw the picture like μt is the mass distribution, and here is this is μt, and then when we have the evolution of this distribution, of course it change the place and so on. But what we can do, one can try to move more or less all at the same place all these measures for different. This is T1, T2, T3. To move like the following. Suppose that I do this one. I do some shift. Then I will get the following. This is the measure corresponding to this T2. This will be the measure corresponding to this T3. And then we will get the compact family. So this is the idea. Now let me show you right definition, and we will discuss it. So let us say that the family mu alpha belongs to some set of indexes A. This is a family from M. You remember, in such a way we denote the family of all probability measures on the space Rg. Is shift compact if there exists a family of U alpha. This is the family from Rg such family mu alpha minus U alpha, alpha belongs to A, is compact. I say compact, but usually when we discuss the family of measures, it means precisely speaking that its closure is compact. But we usually say that the family of probability measures is compact in this case. Is compact. So here I use such notation, which maybe is evident. This is the shift of the measure on the vector. So this shifted measure mu alpha minus U alpha from the set delta is equal mu alpha from the set delta minus alpha. So this is the definition of the shift, and we see that it is exactly what we discussed before. So we can expect that we will have such a behavior. We can have such a asymptotic behavior for the process mu t. So let me demonstrate to you some theorem. This theorem was obtained by me and my former student Maria Karlikova, and let me write the conditions precisely. So okay, so let us consider again the equation of this interaction, which we discussed. Dx ut into hx ut dt plus rt bx ut p w dp dt. As before, we have set all initial conditions. Mu t is equal to the image of the initial measure is the vector x. Suppose that we have such dissipative such a condition that h u1 mu minus h u2 mu multiplied with the u2 minus u1 is less or equal to some constant a not u1 minus u2 squared with positive constant a, and a must be bigger than Lipschitz constant for a and b related to both values x and mu. So I just say like this plus c2. It is not necessary to discuss what is the Lipschitz constant because we did this previous time. Then we have exactly the following conclusion. Under this condition, the measurable process mu t, this family is compact in distribution because they are random in distribution in the space M2. Of course, one can put here different powers and get the same statement about the space, not M2 but MP, where B is greater than 1. What I have to say, you see this condition. This condition says us that our force H does not allow to our particles to go one away from us. But there are no any fixed attracting point for our particles. Just this condition does not allow two particles go away very far. Comparatively with noise and this is actually usual condition for the dynamical systems, but only one difference is again I must say that we have no any attracting point, and of course we can produce a very simple example where we have this condition but we have no attracting point. Very easy, and for example, for play. Here is the simplest example when our particles are floating parallelly. This is just dWt, where this is one fixed linear process. Then what we have in RD, we have the formula. This is our initial mass distribution. It's flown like trajectory of linear process, and of course one cannot expect that this family of measures will be compact, but it is trivial that we can move it, and it will be in our example even the same. So our theorem says us that we can find appropriate conditions to have such a sheaf compactness for our measurement. But still, one can ask the following question. What about stationary regime for such kind of equation? And here is a very interesting story. So now let us discuss a little how we can find stationary solution to our equation. Let us write it again. Here is dx ut equal ax ut dt plus integral with respect to r dv x ut p w capital T. And now I am not writing any initial condition because I'm wanting to discuss the following case. Mu t still is the image of some measure d0 under the naked xt, but we have no any initial condition. Now w is defined. W is defined on RD multiplied by R. This is not half line, but almost the real line. And the solution to this equation is the adapted process to the flow of W such that if we fix some interval T1, T2, then integral form of this equation holds starting from T1 up to the one for any intervals. This is the natural and usual well-known definition of the stationary solution to stochastic differential equation. And now let us ask when we can have such stationary solution. This is the first question, and this question leads to the much more interesting and much more valuable question: how we can get this stationary solution. And here I recall you the procedure which is known from the well-known book of Khasminsky. So this procedure is going to 70s of the previous century, and this procedure looks like follows. We just consider timeline. Here is 0, and what we did, what we are doing. Let us take the point t0. Let us take the point t0. Consider here RD and solve the Cauchy problem for our equation starting from the point t0. So let us consider Cauchy problem for our equation starting from the point t0. What we get under good condition of the coefficients, we get the solution, and this solution will be denoted x t0 ut and mu t0 t. So we get the pair for every t0. Then what we did, we just consider t0 going to minus infinity, and we expect that under this under some assumption of the coefficients, we will have the convergence of x t0 u point will converge to x t0 u point, and also the same will happen with mu t0 will converge to, oh, excuse me, this point, mu point. Why I am putting here point? Just to emphasize that we will have we must have the convergence, not the fixed values of our process, but we must have convergence in distribution as a random process. Of course, usually we proceed as follows. We get some convergence of the values at the fixed point, and we can guarantee the big convergence by using some kind of common condition for our process. But here we face two new problems. One problem is very theoretical. You see here I have the convergence of measure value processes. So what we need, rigorously speaking, we need to have the criteria of the big compactness of the measure valued processes. And of course, there are a lot of such criteria. Some of them goes to, by the way, to Skorokhod paper related to super diffusions. Other well-known criteria is Aldous criteria, which was produced when we discussed Levy-Biot processes. But for our purposes, I introduced new criteria for the compactness of the measure valued process, and let me show you it, because it is very useful exactly for such situation. So let us say a few words about the weak compactness criteria for measure valued processes. In order to simplify situation, I will consider the processes from this one. C01 M. So what is it? This is a space of continuous functions with measure valued argument in RD, and continuity is with respect to the Wasserstein distance of OD0, because here is there are no any p of ODC. So how one can construct the criteria of the compactness? What we have to do? We have to control several things. We have to control in some way that our measures are close on the sets, say, inside of RD, and we have to control that our measures don't go to the infinity. So we will not lose the weight inside the RD. How to do this? One can proceed as follows. Let us consider the family of two families of functions. One family is the function of C infinity RD, and this is a family of functions which define the measure. So it is smooth functions with a compact subgroup, such that if we have the equality for any k, then mu is equal. Yeah. One can easily find such a family for the space-time. Another family will control for us the tails of the measures, and it is organized in one-dimensional case. I will draw the graph as follows. We have the ball minus r, and we have 0 inside the ball, and then such a here they are smooth. For example, here is r plus 1, minus r minus 1, and here is 1. Yeah. So these are such a kind of function, and we can find such a function taking instead of r natural numbers. Yeah. So this is a family of functions which will control for us the tails of our measures. And it occurs that for the family, if the following condition holds, we have the compactness. Let me show these conditions. As before, I am saying the family of measurable forces is weak compact. It means that it closes compact, as you know. So the condition, the theorem is following. The family psi alpha belongs to some set of indices of random elements in this space C01 M is weakly compact. If and only if here we have the following if and only the first for all k such a family f here integral fk psi alpha t, here is point. This is a random process. k greater than 1. Oh, excuse me. There is alpha. Alpha belongs to A. This family is weakly compact. Is compact in C01. And second one is that such a family JK psi alpha. Here alpha belongs to A and K greater than 1 also is weakly compact. Is compact. And the last condition, I will revise this one, but we remember that we discussing the weak compactness of the family psi alpha. And the last one condition is the following, that for all t, for all epsilon which is greater than 0, we have that the sup with respect to alpha probability that this one jk psi alpha t is greater than epsilon tends to 0 when k is equals to. So let me comment these three conditions. The first condition is very natural. We said that the set of k are the set of determinate measure functions. So one can expect that fk can serve as some in some kind as coordinates of the measure. What we need, we just say that every coordinate is compact. Yeah? This allows because we have here just the countable family. We can find convergence subsequence, yeah, for every coordinate. But we must control simultaneously the tails, and this is the condition. You see, we just ask that all these functions which are related to alpha and k together organize the compact family. The last condition say that under fixed t, by the way, it can be substituted not for all t but for one t as usual. Under fixed t we have our measure organized relatively compact family in R. So what is the good feature for us for in this criteria comparatively to well-known Aldous criteria, for example? The feature is following. We have no supremum on the side of probability. You can compare this criteria with other one, and you will see that usually people wrote this supremum here, or here substitute these two conditions, putting supremum inside. And usually it is hard to work with the supremum inside. But in our case, when we have such a criteria, the further work can be very straightforward. Why? Because we discussed these are Lipschitz functions. So we can apply usual machinery of A2 estimation, of P estimation, because we work with semi-martingales, as we have seen from the definition of our solution. So one can more or less straightforwardly get the weak compactness of the solutions to our equations interaction. So I just wanted to present to you this criteria because it is very useful exactly for the equation consideration. Then what one can suppose to obtain in this case? One can suppose to proceed this form. Let us we consider the equation Ax dt plus dx mu t p w d and how one can look for a stationary solution. Let us recall say the case of one particle. One particle case can be discussed as follows: x t equal ax t dt plus dx t dwt. And what is the most simple and most evident condition which gives us a stationary solution for such kind of equation? Just simplification of this coefficient like this one: minus alpha xt plus some f of x. If alpha is relatively large comparatively to the Lipschitz constant of f and b, we then have stationary solution. For example, in case absence of f and b equal to 1, we get Stein-Uhlenbeck process. Yeah. So one can try to do here this. And it occurs, by the way, I think that one of my colleagues, Andrei Pilipenko, did this, that if we consider here the same trick, suppose we substitute this by the minus alpha xt plus some f of x mu dt. Then one can get the stationary solution using Khasminsky procedure. And we can say, okay, we get the desired thing. We have the stationary solution, but it occurs that this stationary solution has very interesting structure. Let me recall you that we have the family of particles which start from any point of our space. So when we consider this Khasminsky procedure, so this is a T, this is RG, and this is a point P0 which we later push to minus infinity. Then we have the formula. There are some random trajectories, but these trajectories are not coalesced. Yeah, we have the following picture. Even under good conditions on smoothing for coefficients f and b, one can say that this such vectors are diffeomorphic. Yeah, only what one can expect. Only one can expect that the behavior is the following due to this alpha. like the following. So they became to be close and close one to another, the trajectories. And what happened at the infinity? Now one can understand. If this is for some zeros, then when we shift this initial condition, this initial time to minus infinity, we will get here just a random point. So the stationary range for such equation, and it can be proved that it is unique stationary range, is the following. We have here a point which is floating around the space. From the point of view of some future application of the turbulence theory, we discussed, for example, this Helmholtz approximation of Euler equation. Yes, it is not nature. It is not nature. Maybe this can happen in the nature. Yes, when we have big star mass distribution and it collapses into big one. But in general, it looks non-nature. So after this, it was proposed a lot of different modifications, but maybe I have no a lot of time to discuss these modifications. I just mentioned that, for example, I consider the case when actually, which is very close to Kuramoto system, when every point x u t has its own attracting center. So we just say that every point in our space is moving correspondingly to the outer force, random media, and attraction to its initial point. In this case, one can prove the existence of stationary solution and have a good properties like absolute continuity even of this stationary solution with respect to the back measure and so on. Another idea is to consider infinite measure with very special conditions instead of mu t, with very special conditions on it. Then also it can be produced in the book. I think, am I right? I think in the work of Pilipenko and his former student Maxim Tantsula. So one can find stationary machines for equation with information. But now it's the last time which I have. I want in this lecture I want to discuss some other topic related to equation with information. Namely, let us came back to the Markov structure of our equation. We have the we call it again. We have the equation like the following. Here we have initial condition x u0 is equal to and mu t is equal to the image of mu 0 then one can ask, what is the Markov structure of this solution? What I mean? You remember fluid and very large theory of the diffusion process. When we have here only dependence on the position of the particle at the present time, we obtain Markov process, which is called diffusion process, and there are a lot of machinery for investigation of the related semi-groups. There is a very fruitful relation between the problems from theory of partial differential equations and diffusion process. Let me recall you Feynman-Katz representation for solutions to boundary value problems and so on. So there are large and fruitful theory related to such kind of to Markov nature of such kind of equation in the extent of mu. Now, what we can expect? We already said that this mu t is responsible for interaction between particles. So, if we fix just one particle, so if we fix starting point, one cannot expect that its motion will be marked. And it is not hard to construct corresponding examples. But where we lose this Markovity, because when we have the random medium, which is described as usual by the measures independent increments with respect to time, then one can expect Markov structure. And of course, we have it here. What processes occurs to be Markov? Here is the process mu t itself. Of course, mu t is Markov. The reason is very simple. If we have a good theorem about the existence and uniqueness of the solution to Cauchy problem, the way how to prove the Markov structure of this mu t is very well known. We just fix the moment of the time, then consider mu t as the initial condition for the further considerations. So it's okay, but it occurs that we also have another family of Markov processes. What is it? If we fix a few starting points, then such process mu t x u1 t x un t t is greater or equal to 0 also is Markov. So we have such a property that we have Markov process. We have such property that together with this distribution family of particles organize also Markov process, and we have this the last property. We have this last property. This is our expression of mu t. So now, having this expression, one can forget about the stochastic differential equation. Having this condition, one can forget about the stochastic differential equation. Even one can forget about the Euclid space. What we can consider the process mu t together with x mu t x t. We can consider it in a general geometric space and say it is evolutionary. Markov process, if we have these conditions. It was my definition proposed by me, and one can ask how one can build these processes and how they are related to the known processes and which properties these processes have. And let me say a few words about the construction of this process and their properties. First of all, let me recall that usually when we have the Markov process in arbitrary space, one can start its description from the family of transition probabilities. So, in our case, we can proceed in the same way. But, as I recall you, if this is the phase space, then mu t will take place in the space of meshes. And because we study stochastic process, not the formal algebra, it is hard to study transition probabilities in the space of probabilities. It is, of course, it can be done, but maybe it's not an appropriate way. We usually want to have much more things. And let me introduce you the family of such things. So it occurs that to describe the evolutionary process, it is enough to have the family of the following probabilities. Let me define this probability. I will think about the homogeneous time process. So when I say transition probability, I will index it by the one time argument t, which means that we move from some time point to this point plus t, and here is mu, and here is u1, un, and here is beta, which is the probability that mu 0 is equal to mu, and the vector x u1 t x un t will belong to set theta. Here is set theta from the power of this. So you see, such kind of transition probabilities, such family of probabilities, is much easier to understand, much easier to handle, because it is related to the motions of particles in the initial phase space, not in the space of meshes. And it occurs that such family, under appropriate conditions, can give us the evolutionary random process. How it can be constructed? Of course, we need some continuity, and this continuity will be forward. This transition probability must be continuous with respect to you and with respect to you. And with respect to you. Then, what we can do? Roughly speaking, because I have not a lot of time, else, roughly speaking, we can proceed as follows. Using this family of probabilities, one can construct evolution starting from the discrete measures, like this, Tk, beta, uk, from k equal 1. And it can be proved that for such initial measure, mu0, when we start from this point uk, for particles x, u1, t, x, u, and t, u, and k, t, we can say that they are Markov processes, they are organized Markov processes. After this, they manage the behavior of all other particles. Like, this is, by the way, like in life. If you have big, heavy guys, these guys manage the life of all other people in our space. This is life. We have the conditions under which we have such evolutionary process. Then one can ask about the properties. And there are, of course, a lot of interesting properties of this evolutionary processes, but I just want to mention one just for 2 minutes. And this property is related to well-known property of diffusion process. Let me recall this. If we have dx, the usual stochastic differential equation, in simplest case, bx dwt, then the solution of this to this equation have the trajectory of linear process, but it moves along these trajectories with different speed, and this speed is managed by this diffusion coefficient. So one can think that one can get the diffusion process from linear process just changing the time. Exactly the same happened in the case of equation acceleration. Let me show you. Let me show you just the last statement. Suppose we have initially the usual stochastic differential equation ax t plus here dx dwt, and let us consider the initial measures this. One can consider mu t, which is equal to mu0 to image x, where I solve Cauchy problem for this equation starting from any point of the space, but there are no any interactions. Now let us take the function j, which belongs to C infinity b, and j is non-negative. Then let us define such an additive functional kappa t. It is equal for the solution from this process mu t is the integral from 0 to t of this j mu s dx. Then it is natural procedure in the Markov process theory. One can consider initial process mu t, xt, and make the change of the time, and this change of the time like kappa minus t. Yeah. And it occurs that this new process, xu kappa minus t minus 1t, mu kappa minus 1t, will satisfy equation with interaction with new coefficients which depends on mu. Yeah. We will get equation with interaction with this substitution of the time. And it is natural because you see, when we speed up our process, when we get the domain where J is positive, or maybe we just make it slow and so on. But it depends on the whole mass distribution of the time. So, in some special cases, evolutionary process can be obtained as a change of the time of the usual flow related to ordinary stochastic differential equation. But of course, this is not a general case. Not all evolutionary processes can be obtained in this kind. So now I'm stopping with this lecture, and the aim of the second lecture was to discuss just the line of investigation related to this equation with interaction. I suppose that two next lecture will also show you the application of equation with interaction, where next speaker, Yasmina Georgievich, will show you the backward stochastic differential equation with interaction. This is all what I wanted to say today. Thank you for your attention. Maybe somebody have questions or comments, please.
May I make two comments about stationary solutions?
Yes, of course.
So when I studied, so these are two funny stories. When I studied stationary regimes, I explained to my wife this, and she told me that this is very unnatural, that all particles are collected in one point. And her argument was as follows: if this is true, then all garbage in ocean will concentrate in one place. And next day we read news that there is like a continent between Australia and Asia, a continent of garbage that is concentrated. So this model is, so sometimes this happens. And another comment was as follows about particles that have its point of attraction. And that time I had a lot of hair, and my example was as follows: every hair on a head has its own point where hair attached to a head. And when you run, so your hair moves, but it but not so much. And every hair try to, you have interaction, but it cannot go very far from its point where the hair is attached. So there are some examples of such situation.
Yes, surely I think that this idea of the center of attraction is good. Surely. Thank you. And maybe some other questions or comments? Okay, if there are no questions, then we finish our work for today, and see you next week with Yasmina lectures. Bye.
Thank you. Goodbye.
Thank you. Bye.